All right, today we're jumping into one of the most mind-bending ideas in all of physics, black holes. And we're going to tackle a paradox that pretty much turns our common sense completely on its head. So let's just get right to it. Here's the big question for today. You would think a bigger, more massive black hole would be way more dangerous, right? I mean, that just makes sense. Well, it turns out that when it comes to that moment you cross the point of no return, the exact opposite is true. So how do we wrap our heads around this? Well, it all comes down to a process with a truly fantastic name, spaghettification. It is, quite literally, the universe's most extreme spaghetti-making machine. Okay, so the key to all of this is something called tidal forces. You already experience them. Here on Earth, the moon's gravity pulls just a little bit stronger on the side of the planet facing it than the side pointing away. It's a tiny difference, but it's enough to stretch the Earth and give us our ocean tides. It's a pretty gentle effect here. But near a black hole, yeah, gentle is not the word I would use. See, because gravity gets so much stronger so quickly the closer you get to a black hole, the pull on your feet would be thousands, millions, billions of times stronger than the pull on your head. You'd be stretched out vertically while being squeezed in from the sides, just like a piece of dough being rolled into, you guessed it, spaghetti. Now, here's where it gets really weird. This force changes dramatically depending on the black hole's size. So let's compare a small, stellar mass black hole with a supermassive one. The key difference isn't just the mass, it's that the edge, that point of no return called the event horizon, is way, way closer to the super dense center of the smaller black hole. And this is where the paradox just smacks you in the face. Look at these numbers. At the edge of that stellar mass black hole, the tidal force would accelerate you at 19.6 billion meters per second squared. You would be atomized instantly. But at the edge of the supermassive one, the tidal force is actually weaker than what you feel just standing on Earth's surface right now. You could literally float right past its event horizon and not even notice anything was wrong at first. So we get why small black holes are deadlier at the edge. But where do these cosmic monsters even come from? Well, it all starts with the life and, more importantly, the death of giant stars. Picture this. A truly enormous star runs out of fuel. Its core collapses under its own staggering gravity, and that triggers a cataclysmic explosion called a supernova. The star's outer layers get blasted out into space, but what's left behind is this incredibly dense core. But that core has a choice to make. Is it going to stabilize as a neutron star, or will it just keep collapsing forever and become a black hole? The answer comes down to a critical tipping point in physics. It's called the TOV limit. Think of it like a cosmic scale. If the leftover core's mass is below this limit, a quantum force, which is basically just matter putting up a final fight, refusing to be crushed any smaller, can push back against gravity. You get a stable neutron star. But if that core is too heavy, gravity wins. Game over. Nothing in the universe can stop the collapse. And according to the latest calculations, that magic number, the TOV limit, is about 2.928 times the mass of our own sun. So here's the bottom line. Any collapsing stellar core that's heavier than this is absolutely destined to become a black hole. And this table really lays it all out. If you're below the limit, say at 2.5 solar masses, you get a stable neutron star. But right at the limit, something totally bizarre is theorized to happen. It becomes a black hole that actually has an invisible neutron star still trapped inside. And then, get this, if the core is too massive, more than about 7.15 solar masses, the brand new black hole is so unstable it just immediately explodes. Okay, so we've seen how these monsters are born. Let's get back to our journey. Let's say we've survived that surprisingly gentle crossing into a supermassive black hole. What happens now as we fall toward the center? Well, the physics gets even crazier, and the best analogy might be something you find right in your own kitchen. This incredible quote comes from physicist David Garfinkel. He explains that as an object gets close to the center, it's not just stretched in one direction anymore. It is violently kneaded, squeezed, and twisted by the warping of space-time itself. The physical force doing all this cosmic bread making is called shear. It's the part of gravity that actually deforms an object's shape. And unlike spaghettification, which is a fairly straightforward one-way stretch, shear near the singularity is total chaos. It's multidirectional and completely unpredictable. Physicists call this the Mixmaster dynamics, and it's a terrifying dance. First, you're stretched vertically while being squeezed horizontally, but then the directions of this force rapidly and violently flip, and suddenly you're being squeezed vertically and stretched out horizontally. This chaotic process repeats over and over again, getting faster and more violent the closer you get to the center. And the scale of this is it's hard to even process. Between each of those chaotic changes in direction, an object's shape could be distorted by a factor of 100 trillion. It's a level of violence that our brains are fundamentally not built to comprehend. And this brings us to the final stop on our journey, and really the ultimate question in all of black hole physics. What is actually waiting for us at the very center? For decades, Einstein's theory of general relativity has given us one pretty chilling answer: a singularity, a single point of zero size and infinite density. It's a place where space-time itself just ends. And it's a place where all of our known laws of physics completely break down. But a lot of physicists today think that when your theory gives you an answer like infinity, it's not describing reality. It's just a sign that your theory is incomplete. When things get this small and this dense, quantum mechanics should take over. And that theory paints a very, very different picture, a much fuzzier picture. This puts us right at the cutting edge of science. On the one hand, you have the classical singularity, a hard dead end. On the other, from string theory, we get the fuzzball theory. It suggests there is no single point of infinite density. Instead, the entire black hole is a tangled, vibrating ball of fundamental strings, and crucially, space-time doesn't end at all. And this opens up a final, absolutely profound question. We often talk about the Big Bang itself starting from a singularity. But if this fuzzball idea is right, if singularities don't really exist in nature, that changes everything. It could mean our universe didn't just appear from nothing, and it could mean that time itself had no beginning at all.